Hi, my name is Noah Bailey, and today I'm going to be going over my 120 volt AC load measurement device. This design is a part of the ECE5000 electrical engineering design course at Memorial University, where students are tasked with a project each to design and implement and test. As I mentioned, my project is a 120 volt AC load measurement device. It measures and displays voltage, current, power, and energy, and it displays this information to an LCD as well as an SD card. It is based all on Arduino, or in this case, an Elegoo Uno R3, which is essentially the same thing as an Arduino. And this is the third stage of the design process, implementation, where students present their first prototype of the design and show it off, go through how it works, and give an overall demonstration. So let's jump right into the components. Here is a look at the design on a larger breadboard. This is set up for ease of use, ease of view. As I'm showing here, it could easily fit on a mini breadboard or a small breadboard, as all of the components use one single rail for power. The first component that is being highlighted is the Zmpt 101B voltage transformer. It can run up to 250 volts RMS, and it transforms it, it rectifies it, and it sends out one single analog signal from 0 to 5 volts into the analog port. As I'm showing here, it goes into analog 0. It's attached to two probes, which are attached to my load to be measured in parallel. And on the contrary, we have the current sensor, which works using the Hall effect. I must apologize here for the focus of the video. This is the ACS712. It must be measured in series, so we have two probes attached in series to my circuit. And as I mentioned, this will use the Hall effect to measure the current. This has a single analog output as well, which is in port A1 of the Arduino. Both of these devices are powered by a 5 volt VCC and ground. Next up is the SD card module, which currently has a micro SD in it. It has 6 ports, which are chip select, clock, MISO, and MOSI, a voltage VCC, and ground. MOSI is master out slave in, and MISO is master in slave out, and they are connected to the digital pins of the Arduino. Somewhat related to this is the button and LED. This is for the safe eject feature, so that no data is corrupt or lost or damaged when the SD card is ejected. And then the last component of highlight is the LCD. Apologies once again for the focus, but we can see here that it is reading a 0 because there is no complete circuit, and the circuit is off, and that is also connected to the digital ports. It features a potentiometer, which controls the contrast of the screen, and it also has a 220 ohm resistor coming out of one of the ports just to drop some voltage for safety. As mentioned, these all go to the digital and analog pins of the Arduino, which is currently being powered by my laptop as seen, but as mentioned previously, the final design will likely be powered by battery, so that all of these can be encased within the housing. Alright, so now that we've taken a look at the components, let's jump into the code and we'll see how this design works. Alrighty, so as you can see here, I've pulled up the code, and it is quite long, but we will go through each part individually and develop an understanding of what it all does. So let's start with the initial setup, which is this section right here. So this section involves including the needed libraries, which are Liquid Crystal, SPI, which is communications protocol, and SD. It involves setting up the file for the SD card, establishing the button and the LED for the safe eject of the SD, setting up the LCD screen to its respective ports, and then establishing some variables for the most part that are going to be used when we go to calculate the voltage and the current. So this involves setting the analog pins to be red for the voltage and for the current. It involves setting sample reads, which is how often that the voltage is going to be sampled and calculated. It involves calibrating the Zmpt 101B transformer with a voltage offset value. Alongside of this, you also have to calibrate the transformer with a potentiometer located on the transformer, but that is done previously, and so these also must be calibrated. There is a sensitivity, which is model dependent. In my case, I have the 20 amp model of the current sensor, so we use a 1 in the code, which equates to this value here. And then we set up our variables for power, energy, and total energy. And then we do the void setup. This is a function that returns nothing. It turns on the LCD, establishes the pin mode that the button is an input and that the LED is going to be the output, establishes our button state, which is going to be a digital read of the button pin, and begins the serial monitor. And you can see here, initialize SD is commented out. This is for testing purposes so that I don't have to continually move back and forth my SD card. I just skip this step if I don't have the SD card in, but in the real code, it would evidently be like this to work the SD card, as will be seen in the demonstration. Then we jump into the main loop. This is where the samples are taken, the calculations are done, everything is printed to the serial monitor, printed to the LCD, sent to the SD card, and the SD card is constantly being checked to see if it is ejected properly, which we will get into in a minute. So we can see that at the beginning of every loop, it reads the digital pin to see if the button has changed state. This section here is all about the sampling at the rate. We can see every 0.2 milliseconds is taking one reading. The sample value, including the offset value, is read. The total analog values for each thing are taken. And then essentially, the average value of all of the sample readings will be calculated to give out a final RMS voltage here. This is where the second offset comes into play. The current is also calculated here using similar equations via the analog read and the sensitivity. And then these values are used to calculate power and energy. Given that we know this occurs every 0.8 milliseconds, we can multiply by 800 milliseconds, we can multiply by 0.8, which is the seconds equivalent, which will give us joules. And then this energy is added as a running sum for every sample. Here are all the serial prints. Here are all the LCD prints. Here are all the data bits written to the file. And then this resets the sample sum so that the process repeats. But down here we can see that if the button state goes high, eject SD is called, and the LED is sent to high so that we can tell that it is safe to eject the SD card. So if we come down to the SD card section, which is the final section of the code, we can see that eject SD, which we just witnessed in the code, just closes the file, delays for a second, writes the LED high, delays for 10 seconds, and then writes the LED low. So when the LED is on, we know that it is safe to eject the SD card. The void initialize SD is what we saw called above, commented out. This just sets up the SD card, makes sure that it is attached properly, formatted properly, working properly, communicating properly. This is essential before using the SD card. So that's a bit about how the code works. Let's test a load and see how it works in real life. Okay, so here we're going to jump into the demonstration portion, and we're sort of going to go section by section through this. Firstly, you'll notice that I essentially already have my load connected. I don't have the current connected though, so it will not measure anything currently. Step 1 is turning on the computer to connect our board and plugging in the board. Here I am checking to make sure that the initialize SD is actually being used in the code, and it wasn't, so I fixed that here. Upload the new code really quickly, and then I'll open the serial monitor here, and it's hard to tell, but you can see that initialize SD card comes up, and then initialization done, and then some of the values start to print to the serial monitor. They're all zeros, as I mentioned, because there is no complete circuit, there is no load being measured. So here's me demonstrating how the safe eject SD works. You can see the LED comes on, and while the LED is on, it is safe to eject the SD card. And then as the light is on, the readings are not being taken. Once the light is off, the readings will continue. So that's how the SD card system works. Now we're going to take a look at the actual measurement process of the device. So here I am just reinserting my SD card so that the code continues to work, turning the system back on. And now the LCD is on and the values are once again still 0. Here I'm going to give a close-up of the values. It is a bit hard to focus on the LCD screen just due to the nature of the camera, but you can, for a moment here, see that the values are 0. You can see 0.03 amps of current. That is just a phantom current due to the sensitivity of the device and other external factors. Now, what I'm going to do here is connect up my probes. So the voltage sensor first in parallel must be across both terminals of the lamp because we want to measure the voltage in parallel. It's hard to see here, but I'm connecting the two terminals to the base of the lamp here across the lamp. Then the current sensor, which are the other two probes, must be connected in series. So I have the wire split from the light into two, and I connect my current sensor in series. I have it connected to a power bar, which is currently turned off, so it is safe right now. There we go. The power bar is on. Now it is live. I will touch these together, and the light comes on. You can see it glowing down there on the floor. And then I will back up and show the light with the camera. So as you can see now, the values that are being read, once again, hard to see the screen. We are measuring a voltage of around 125. The current seems to jump around a little bit. 0.8, 0.5 amps, 0.16. We see the powers fluctuating due to the current fluctuating, and the energy is continually going up as the device is running, since this is a running sum. And here is just the simple connections to the load. Here I am opening the serial monitor, and we will see that it is also printing to the serial monitor. We can see here that the SD card is initialized. The focus does not tend to focus on the screen very well, but here we go. There are the values that are being pumped out, and they match the LCD. And here I'm going to safely eject the SD card once again. The light will come on. It is safe to eject. I will pop it out. And now let's jump over to the computer and see what the file looks like. So as you can see here, I've opened up the test file, which was used from the SD card. This is the file that was produced by the code. After I safely ejected the SD card, put it into my computer. This is the file that we see. These values are the most recent ones here. You can see the voltage, the current, the power, and the total energy for each of the samples that we saw on the LCD and to the serial monitor are printed out here. If we scrolled up, we could see all of the previous zero values being read, and even up at the top, we can see the initial testing of the SD card just to make sure that it was working. One thing I would like to do in the future actually is clean up the way the SD card is formatted, maybe add some timestamps or some better organization of the values, just so that it's not as messy and as cluttered. But where this is the first prototype implementation, for now, it's just working and getting the correct values that it should be getting. So now that we've taken a look at the SD card, let's continue on. Alright, so the next part that I want to talk about is the housing. As I mentioned, the larger breadboard that was being used for the demonstration is not going to be the final breadboard that is used in the design. This is because the design is going to be encased in some form of housing, which will keep it protected and overall make it look much nicer. This will likely go on something along the lines of a regular breadboard or a breadboard mini. As you can see, I'm highlighting here a regular breadboard or perhaps a mini breadboard, whereas currently it's on the larger one. And the larger breadboard was mostly used for demonstration due to the ease of access and the easy connection of the probes that I was using for testing. But here you can see the housing that I created for the first implementation. It's a simple wooden box with one open face just so that there's ease of access. The final design will likely be 3D printed and feature an opening and closing lid, but will look similar, maybe perhaps a bit smaller. I didn't want to waste time, money, or resources on something that may not suit the final design, so my first implementation is made of resources I had. As you can see here, there are 4 legs that it can stand on. One face is left open. There's a slot cut out for the LCD, as well as numerous slots that may be suitable for the probes, button, LED, SD card, and so on. I'm just highlighting some of these ports here and demonstrating the space on the inside. The components will all be held inside safely, perhaps secured down. And as can be seen, a regular breadboard, full-size breadboard, does fit nicely and leaves room for the other components and could even be secured down, perhaps in a bit smaller of a container. And there is a port left on the bottom, perhaps for running power, as currently it is run by my laptop, but in the future it may be run by a battery. But this is just a general overview of the first prototype housing that I created. Alright, so now that we've looked at the components, we've looked at the design, we've looked at the code, we saw the initial housing, we saw a little demo, what's next for the project is the big question. And so essentially, what are some things I would like to improve? What are some things I would like to change? What are the plans for the future of this project? So I've actually got a dimmer switch, which is planned for the testing phase so that we can adjust our values given a load. So we will attach the dimmer switch into the load and then change that value and observe how it affects our values on the outputs. Also, as I mentioned, the housing is just a prototype, and the final housing will be different size, slightly different ports, 3D printed ideally, fully enclosed with a opening and closing lid. I'd like to clean up some of the code, maybe get some of the sensitivities down, get some of the values a little bit more accurate. As we saw, the current readings tend to jump around a lot because the current sensor is very, very sensitive. But that's just something that can be worked on in the code and tweaked in the sensor and the way that it is wired up. I would like to obviously move from the large breadboard down to a small breadboard, perhaps even a breadboard mini, if I can fit all of those wires and connections onto it. And that's about it, really. It's just general cleanup, adjusting values, testing the capabilities for different loads and for different values, and observing if it acts the way it should in all of those different situations. And we will see that in the further parts of this design project. But for now, thank you for watching. I hope you've enjoyed, and that's it. Thank you.